That's important. So moving on. So support and normal. These are quite a bit simpler. The whole point is these forces are whatever they need to be such that the two objects do not overlap. As a funny joke, it's probably not very funny, but it's just an interesting joke that illustrates this. Ghosts, right? Ghosts can overlap, so that means ghosts cannot provide normal or support forces. The idea is a ghost cannot push on you. So I always think it's funny that ghosts can walk across the floor, because the idea is, well, a ghost can't push on another person, they can't lift a tool, they can't push a button on a computer, they cannot stand on a floor. The floor cannot support something that it can't push against. Yeah, so ghosts are kind of strange. Okay, so this really is an aspect of how two things can push on each other. Yeah, so when my two hands push against each other, the idea is they can't push through each other. And that's because as their materials get close to each other, something about the materials repel each other. So it's a repulsion. Okay, so here is a couple of examples. So let's say I've got a box and it's on the end of a rope. And what I'm doing is I'm very slowly lowering this box down onto a scale. So before the box can contact the scale, so before there's contact, there's no reason for the scale to put any force on the box yet, because they haven't gone in contact. But if you do this really, really slowly, at some point, the box has just touched down on the scale, so the scale might read 2 newtons. Let's say this is a 20 Newton box. And as you continue to lower the box down, right, you're lowering the tension in this rope. So you're doing this very slowly. At some point, the scale will read, say, 15 newtons because it's bearing more of the weight of the box. The rope is not having to try as hard. And then at some point, the rope can go completely slack and the scale will read all of that force. So this contact that's happening between the scale, the top of the scale, and the box hasn't happened yet. It's only 2 newtons strong. It's 15 newtons strong. It's 20 newtons strong. It's just whatever it needs to be such that the box doesn't overlap with the object. So this is a simple... oh man. So this contact force is just whatever it needs to be such that the box doesn't overlap with the scale. If you were to drop the box so that the box has actually got a lot of motion downwards and it's about to hit the scale, you know what this feels like. If this was you, when you land on the scale, you have to use your legs quite a lot. You have to interact with the scale in a really, really large way so that you don't push down into the scale or fall through the scale. And so here you notice they haven't been in contact yet, but because this box is going to decelerate or accelerate with such a large value, the requirements for the scale can be quite large. So at some point, the box may be interacting with this scale with such a large contact force that the scale is going to read something like 500 newtons instead. This just speaks to really large acceleration. This is what happens when two cars crash. When two cars crash, it's their structures that are trying not to overlap, right? So they yield and stuff. But because of the really large accelerations, right? This car is going to slow down very quickly, and this car is going to slow down really quickly, and they're slowing down really quickly because their interaction forces are gigantic. And so under the influence of those really large contact forces, they can be much, much larger than the weights of either car. You can have really large shock loading forces. These are shocks. Shock loading is a dangerous situation that engineers really need to be very careful about. So continuing with the examples of support and normal forces, here's an interesting scenario. So if these are two different boxes, and you apply a pushing force, say here, so this is a person having a normal interaction with box number 1. The question is what is the contact, or you might say the normal interaction between boxes 1 and 2, as well as what is the contact or normal interaction between, say, the floor and box number 2, as well as the floor and box number 1. There's all these contact interactions going on. You notice that I haven't said the word gravity here, and I didn't say the word gravity here or there or there or there. So this isn't, so gravity may be another force in these problems, but I'm only addressing the fact that two objects can come into contact. So this is a sideways example. These are vertical examples. And then over here, you can have diagonal examples. So inclined plane is another example. Here is a box. It can slide or stand still. It can have friction or no friction. The point is the way that this inclined plane is going to be able to push out on the object. So this is the normal interaction. We could say that's the normal force vector. It's on the box by the plane, for example. But, by Newton's third law, this box is also pushing down on the plane. If the plane can push up on the box can push down on the plane. So I'll go into the center of the plane and say that the box is pushing with a different normal force back down onto the plane. This is the normal force on the plane by the box. These two forces are equal and opposite, and they are Newton's third law pair of forces.